Here we go. So what I'm going to do right now is I'm going to work through the n queens thing. Let me make sure this is up to date. Oh, 10 pull requests. I'm going to work through the n, no, not the max bit string, the n queens GA, and generate some distributions and do some comparisons. I'm going to run the, yeah.
I don't know if they're supposed to, but we can't see.
Oh, yeah, you can't see anything. You're right. What? Laptop? Okay. Thanks for the heads up. I'm glad you said it now. In 161, that like last week, I got like 10 minutes into the lecture and someone's like, we can't see it. It's like, you could have warned me. All right, so I'm going to run the GA in PyCharm, but I'm going to do the distribution comparison on Colab just because I think it's going to be a little easier. Okay, so here is my all right, so here's what I'm going to do. If I run this once, n queens, so what was I saying? Like make it like 20 queens? Population size 100 generations, 1,000, tournament size 2, crossover rate, mutation rate. Let's see how long it takes for one of these to run. There we go. So not too long. Let's try again because I think it was just kind of chugging away. Okay, good stuff. So we could see, wait, is this? This looks like it's running max bit string. Okay, that's the problem. Poor computer. All right, maybe these settings are a little heavy. Okay, that wasn't too bad. All right, here's what I'm going to do. I'm going to put all of this in a big loop. For I in range. Now, in computer science, in programming, for whatever reason, 30 is the magic number. It's not really meaningful in any way. Really, you want the number to be big. But in computer science, we've all kind of decided that you need a minimum of 30 runs to do any proper comparison. That number, understand that number is, as far as I know, it's arbitrary. It's not meaningful, and really this number should be bigger. Realistically, if I'm doing it, I want it to be at least 100. But for the sake of time during lecture, I'm only going to have it be 30, because I think it's, if each one of these takes like a minute to run, even if they take 30 seconds to run right, it's going to take a little bit of time. So print I. So what I'm going to do is I'm going to take the min. What did I call that variable? So all I'm doing right now is I'm just going to I just put this whole algorithm in a loop to run 30 times, and each time I'm going to save the result in just a list. And then I want those results saved. And I'm only going to save the top result. If you want, you can save more than the top result in your results list. I'm just going to be lazy right now, because this is the one benefit of evolutionary computation that you don't get with a lot of other forms of computational intelligence, is when your algorithm is done, you don't have one solution. You've got a whole population of solutions. Some of them are going to be garbage just because of the fact that mutation happened to them on the last generation and they got all messed up. But there's going to be a bunch in there that are good. So you don't need to just look at the best result from your final population, okay? Oh my goodness. All dot append, and then, do I have NumPy imported? Can I ask for min if I have a list? Oh my God. 0. Okay, good. So that works. Population fitness. Okay. So, and then at the end, I want to print all results list. Okay. So I just put that whole algorithm in a loop to run 30 times. I'm hitting run. And right now, I'm just going to print out, this is going to take a minute, eh? Here. It's going to take too long. Let's make it like 50, 500. These hyperparameter values, I'm not, right now, my goal is not, if you're looking at what I'm doing and you're thinking, oh, those are good values, no, no, no. The point, the values I'm using right now are just to make it run in a reasonable amount of time for demonstration purposes. Okay, there we go. Now we're looking a little better. I mean, you can clearly see, even with these values, we're actually finding optimal results for 20 queens, which is pretty crazy if you ask me. Right? I think that's pretty impressive. In fact, they're so good that I'm finding this boring. Let's make it 25 queens. All right. So, let's see what we're getting here. It's still, holy moly. Am I doing something wrong? Because the result, that's the funny thing with AI, you know? When your results are really good, you have to ask, what's wrong? Why is it working so well? Sheesh. All right. All right, so I'll just leave it as is, but here's what I'm going to do. Every time you see those lists of results shown, that is the result of running the GA once. So I'm running the GA over and over and over, and I'm going to run it for a total of 30 times. I'm going to save the best result out of all of these for each run. And then at the end, I'm going to have a list of the best fitness for each run. So I'll have a list of 30, right? Make sense? A list of 30, and each one is the best result of any one given run, of each run, respectively, right? And that'll give us a distribution of results that we can see. Let me go here. I'm just going to do a bunch of imports. I don't know if I'm going to need them all. What else might I want right now? All right. Okay, and then here we go. So here's my distribution of results in the end. They're actually really good. In fact, this might be really boring. Let's make it like 50 queens. It's going to be, okay, just because I want to get interesting results. Bear with me here. Notice, when I made it 25 to 50, look at the runtime. Like, it really does have an impact on the runtime quite a bit. And that's because you got to figure, as n increases, each time we do the fitness evaluation, we have to run it on n, where n is the number of queens. And if I am doing this if I have to evaluate the population 500 times, that's 50 times 500 times n, you know, in terms of total work. So it's going to grow quite a bit. All right, we've got 5 done. And now these results are worse, which is what I wanted. I wanted less good results because I wanted to kind of show what the distribution would look like on, you know, if this was TSP, the distributions would be a lot cleaner just by virtue of the fact that if you're dealing with something where you've got fitness values in the thousands or millions, yeah, you're going to get crazy different variation in results. With N queens, due to the nature of the problem, it's going to be a lot more discrete isn't the right word, but for lack of a better term, more discrete than, that's a terrible way to word it, but okay, we're done 10. We're 1/3 of the way done of run 1. So here's what I'm going to do. I like these settings now. So first and foremost, if I do a run once, and then I say, okay, those are the results, and I like those results, but I want to see what happens if I change the tournament size to 5 and lower the crossover rate to 50. And then I run it again. Now, there is nothing, now listen up, this is important. There is nothing wrong with changing multiple hyperparameters at once, but it makes your comparisons a lot less clear. Because if I want to know the impact of changing the tournament size, but I change the tournament size and the crossover rate, I can't really know which one is responsible for how much change. And on top of that, what makes this even worse is these have so non-independent complex relationships, these hyperparameters, they have crazy relationships that if I have the settings set to this, and I change it to 5 and the results get better, and I change this to 50% and the results get better independently, and then I run it again where I change this to 5 and this goes to that, maybe it gets way worse when you change both. Because these hyperparameters are so inextricably linked to one another that you can never really know. But we do our best to isolate the impact of each hyperparameter independently as best we can, even though we all know and we all accept the fact that it's such a complex, that's so complex, they're so not independent that we just kind of do what we can. But we all kind of accept this, and this is just kind of the nature of any complex system. All right, we're getting there. So what do you think, what should we do for the next run? Higher tournament size, lower crossover, higher mutation. What do we want to do for the next run? Higher tournament, all right. Perfect, I like that. So, tourney 2. Oh, we're almost there at the end. Come on, last one. All right, there we go. So there we go. There's our results. Now, when I run it again, what should we make the tournament size for the next run, just for fun? 10. Woohoo, crazy. That's going to have a lot of selection pressure, but that's fine. Let's see what happens. Okay, great. I'm going to hit run. Now, while that's running, we can do a little something here. So, okay. First and foremost, I require my imports to be in alphabetical order because they need to be, because if they're not, it doesn't make any sense to me. People who don't do them in alphabetical order are crazy. So they have to be in alphabetical order. And then what else should I have? Is that right? Yeah. Let's see if this is running. Okay, looking good. Oof. Looks like the high tournament. From a quick look, I don't know, it's hard to say. Anyways. First and foremost, it's always nice to get some summary statistics for your results. Now I'm trying to remember how best to do this. Is it SciPy? Describe. What's in pandas? I don't want pandas. There's nothing wrong with pandas, but I was thinking of NumPy. Yeah, okay, describe. There. So here, if you weren't aware, is a nice little built-in function, and n-obs, number of observations, is 30, yep. Min-max is 1 and 5. The best result was 1, the worst result was 5, because this is a minimization problem. The mean was 2.63333. The variance is 1.4126, whatever. Skewness, 0.6. Kurtosis is negative 0.5199. You all know what skewness and kurtosis is, right? I know, it doesn't matter. Don't worry about it. It's about like how the shape of the distribution looks. These are some like pretty, what's the word? There's a word, I don't know, my brain's not firing on all cylinders right now, but it's, whatever, don't worry about them. There's a word that I know, or at least I used to know, that would be really good to describe what those words mean. Trust me. But right now, it doesn't matter, okay? Usually when I'm doing this type of stuff, I like non-parametric statistics. Without going into all the details, you know, the average result was 2.6333, but how many of our results had a fitness of 2.63333? None, right? Because that's not possible. So like the average result isn't even a valid, like it's not even possible, which is kind of weird, right? So instead what I would do is dot no. Who's got median? Is it in deprecation warning? Oh no. Use numpy.median. Oh, all right, fine. All right, there we go. So the median result is 2. 2 conflicts. Great. And so when you're thinking of non-parametric, what's nice about non-parametric too, especially when it comes to comparing distributions, it requires less assumptions about your data, which is especially important when you only have 30 observations. I mean, I'm speaking in some pretty big generalities here, but things like median is a little better than mean sometimes. When you're comparing, instead of looking at, is IQR? Interesting. IQR. Maybe I'm thinking of the wrong one. But you might also want to look at like the interquartile range. Like what is the range of, maybe that's like plus or minus 1. Maybe that's what that meant. The interquartile range is where would you find like the middle 50% of all your results, right? It kind of it tells you like, well, the bulk of your results were between here and here with some outliers, right? Looks like that one ran. Oof, from a quick look, it looks like the bigger tournament size had a really big, like a good positive impact, right? Look at that. I'm just going to go up here. So look at this. You look at this, and what is your reaction? Tournament size of 2 had a median result over 30 runs of 2. Your tournament size 10 had a median result of 1. Clearly 1 is a better number, right? So like that is a good observation to make. But you have to remember when looking at a summary statistic that is a data point that's trying to account for 30 data points, right? So obviously there's some information lost there. Do we agree? I have 30 data points and I want to summarize them. So I do it by getting the median and I get one number. One number apparently describes those 30 data points really well. Well, not quite, right? So, okay, let's go to matplotlib and say plot.hist. And I plot it and I get this. Oh, that's terrible. I want bins to be... So there's my distribution. All right, cool. And then here, let's get fancy. T2 for tournament 2. And I'm also going to plot the other distribution against, like I'm going to plot the distributions against each other, right? And now, so this histogram shows the distribution of results. It's showing, okay, the orange one, here, let me say, the orange one, of the orange runs, 6 had a 0 to 1 conflict, 14 had 1 conflict, 8 of those 30 had 2 conflicts, and 2 had 3. If you add 6 plus 14 plus 8 plus 2, you get 30, right? So that is the distribution of the 30 runs. Does this make sense so far? I don't know if again, this is the constant issue I have with all of y'all. Your quietness. Is it because you understand completely and you're like, yeah, come on, I know what a histogram is? Or is it because you're like, I have no idea what's happening? It's one of those two. I don't know. Give me some insight. Is this so far so good? Everyone happy?
I think it's a mix of so far so good and it's 9 a.m.
Okay, fair. That's a good point.
Where did you get the conflict?
Pardon?
Where did you get the conflict? The conflict?
No, my conflict is I don't know if you're like, yeah, I understand. I know what a histogram is.
No, I'd say the conflict on the histogram.
Where's the conflict?
Yeah.
There is no conflict. No, what I mean is I don't know if you understand completely and you're bored or if you're confused as hell and you're scared. But I think we had the best answer here, which is it's 9 a.m. That's the problem. There was a secret third option. All right, so that's the orange histogram. And then the blue histogram, which represents the 30 runs on when the tournament size was tournament 2, we see, well, first of all, none of those runs got the best result. But we see four of them had a conflict of 1. It looks like 13 had a conflict of 2. 6 for 3, 4 for 4, and what's it? Probably 3 for 5, right? So when you add all those up, you're getting at 30. So there's a total of 60 data points represented on this plot. Just 30 of them are in orange and 30 of them are in blue. So now you do the eyeball test. When you look at these distributions, obviously lower fitness is better. So the distribution that's closer to, the left is better. The eyeball test here, when I look at this plot, I go, okay, it really looks like the orange distribution is better, right? It really seems as if, it really seems as if a tournament size of 10 had a really positive impact on the results. Would you agree? Now, here's the kicker. We only have 30 data points from each. And the question I have is, are those distributions really that different? Now this is an important distinction. First, there. I plotted them both in blue for the purpose of, and let's get rid of the alpha. There. For the point to show you, let me put it this way. If I ran one of those algorithms, one of those settings, 60 times, would my distribution have looked like this? I don't know. I really don't know. The point I'm making here is, when I look at this, oops. It looks like they're different. But every time I run these algorithms, I get a little bit different results. Maybe when I ran T2, I got a little unlucky, and maybe when I ran T10, maybe I got really lucky. So the question I'm asking is, did one set of settings I have for the hyperparameters for the algorithm, did it really produce different results? Did it really? Okay? What I'm not asking right now is, which one is better? That is not the question. I want to be very clear about it. The question I'm asking is, did it really produce different results than the other one? Whether or not it's better is not an interesting question for me right now. It's, are they even actually different? So this is where your p-value comes in. Raise your hand if you've heard p-value before. You've heard that phrase. Yeah, come on, you've heard p-value before. Maybe probability value, p-value. Yeah, that's what p-value means, a probability value. You've done your t-test and you get a p-value and you know the magic number is 0.05, right? You've all, raise your hand if you're familiar-ish with these ideas. Okay, 2 people. This is, that's fine. I assume more people would be comfortable with this, but okay. So usually what you do in statistics is, if you've taken like your first year statistics course, they're going to throw a lot of information at you. One of them is, you have distributions, you want to compare distributions, you do a t-test, a student's t-test, that's what it's called. And there's a bunch of variations of the t-test. But you do the t-test and you get a p-value, because that's the result you get from doing a t-test. And then after you do your t-test, you've got your p-value. Then you check if that p-value is less than 0.05, and if it is, you say the distributions are significantly different. That's what they tell you. And then you go, oh, okay. But at no point are you allowed to ask, what does that mean? What does all of that mean? They just told you do this and you're good to go. But they never explain what the hell any of that actually means. So I'm going to try to start explaining what it means. So the question that we're asking is, are these distributions actually different? And we start with the null hypothesis. Raise your hand if you've heard the null hypothesis of the same two people, three people. Okay. The null hypothesis is you start from the position that we're going to assume they're not different. We're going to assume they're the same. And then we do this test. Some test to give us a p-value. Now, the test you really want to do is like a permutation test. And that's what we're going to talk about later in the course because it's intuitive as to what it's trying to do. But the problem with the permutation test is when these stats courses were designed 100 years ago and those textbooks haven't been updated since then, they didn't really have access to personal computers like we do today. So if you wanted to do a permutation test by hand, it would take you 1 billion years. So instead what you do is you do what, I'm pretty sure the story goes, you know Guinness beer? Well, some guy that worked for Guinness beer was like, hey, I've got a way to do it. They figured out some crazy math, and they came up with the student's t-test. I think it was the student's t-test, whatever, a t-test to do a quick and dirty comparison based on several assumptions. But it allows you to get a probability value. Like a permutation would let you get a p-value. But the t-test lets you get a p-value a lot easier. It takes you no time compared to if you were doing what you really want to do. And so despite having computers today, they don't really teach you the permutation test until way later, which is too bad because it actually makes sense to what it's actually trying to do. If you follow the steps of a permutation test, it'll like the test describes what it's a very algorithm-y process. And if you kind of like follow the steps of the algorithm, you kind of get what it's trying to get at. We'll get there later. So instead we do a t-test, which is a quick and dirty way to get a p-value. So there's the distributions, great. So here's what I'm going to do. Now the problem is there's so many t-tests. T-test, independent, and here's what we're going to do instead, because this is really what I want you to do instead. You're going to use a Mann-Whitney U-test, which is a better version. It's not that it's better, it makes less assumptions. So you want to use a Mann-Whitney U-test, which you could use in place of like a t-test. I'm speaking very high-level generalities. There's a lot of asterisks to what I'm saying. If there was a stats prof in here, they'd probably murder me. But just use a Mann-Whitney U-test. And what you do is you give this test the two distributions you want to compare, the two lists. Terney 2, Terney 10. I run it. We get the statistic, which for better or worse right now we can ignore. And then we get this p-value. My p-value is 4.89 times 10 to the negative 6. That's a very small number. And what that p-value is trying to tell me is there is a 4.89 times 10 to the negative 6 chance. There is a probability, that is a small number, right? There's a very small probability that these distributions are the same, right? So we're starting from the null hypothesis, which is we're assuming they're the same, and the probability that they are the same is that. So my conclusion is going to be, no, those distributions are probably they're different. Meaning the set of parameters I used, the set of hyperparameters I used in one versus the other, changing tournament size from 2 to 10 really did produce different results. Okay? The algorithm really was acting differently. Then we can ask the question, okay, so we've concluded that the algorithm is in fact producing different results. Okay, cool. And from our eyeball test, it clearly seems like tournament 10 is better. It's better to have a tournament size of 10. But how much better is it? So this is the second question I'm asking. The first question was, are these different? Oh, and by the way, going back to the p-value, remember I said, oh, that alpha, that 0.05, that magic number. Raise your hand if you, for the 2 of you or 3 of you that have took the stats, you remember 0.05. If the p-value is less than 0.05, you're happy. Well, that is, I don't know if you're aware of this, that's a bullshit value that someone pulled out of their ass and they're like, we're going with this. Because a 0.05 means 5%. And whenever you take a p-value, that if you have something that had a p-value of 0.05, that means that there is a 5% chance that the distributions are the same. So when you have all this scientific literature out there that have p-hacked, raise your hand if you've heard the phrase p-hacking before. 1 person. So a p-hack, 2 people. What a p-hack is, because scientists are stupid, when we're so obsessed, because so many scientists had bad stats profs, and they're so scared of stats, they don't understand what a p-value really means. So they use an alpha value of 0.05, that 5% threshold, to be important. If I was doing some research in some field, and I was comparing my distributions, and I really, really wanted to show that something had an effect, okay? That it really did make a difference. And I had a p-value of 0.06. Or maybe I had a p-value of 0.055. There's a 5.5% chance that the distributions were the same. I'm going to be scared because when the reviewers get it, they're going to be like, it wasn't below 0.05. Reject. Because the reviewers are stupid. Because a p-value really shouldn't be interpreted from the position of, this is the alpha value I'm looking for. No, what the p-value means is, what are the probabilities these distributions are the same? And the context in which you're using it is very important. But anyways, that p-value of 0.05 is also BS because that means there's a 1 in 20 chance that your conclusion is wrong. There's a 1 in 20 chance where you're saying, if I did a t-test on 20 different comparisons of distributions, and they all came out of like 0.05, I'm happy. But that means there's a 5% chance these distributions are the same, meaning 1 in 20 of those comparisons will be like, I'd make a wrong conclusion. So if you've got all this scientific literature that's so obsessed with 0.05, 1 in 20 of them are going to be wrong. 1 in 20 where they're like, there is a difference. It's going to be wrong. But back to p-hacking. P-hacking is when the scientists keep changing things slightly to get a p-value just below 0.05. So their research is significant. Throw the alpha value away. Just what does the p-value mean? It means what's the likelihood of these being the same. And if you look at the scientific literature, people will do meta-analysis of the literature, and you can look at the distribution of p-values, and you will see all the ones with p-values. You'll see a weird spike of p-values just below 0.05, and it's like, well, that's weird. Why would that happen? That doesn't make any sense.
Can P be 0?
Pardon?
Can P be 0?
It can't ever be well, we'll talk about that. So really, no. But we will talk about that. Let's say, when this is what I mean with p-hacking, it's kind of, it's hard to see, but can you kind of see it? If I'd like 0.01, 0.02, 0.05, 0.06, right? What you'll see, it's, come a little closer if you can't see. Let me pick a different marker. You'll see, like, this isn't going to be exactly what the plot looks like, but I'm going to get to what it looks like. You want a value less than 0.05 for it to be significant. So you'll see, like, your distribution, if this is like the count. You'll see the distribution of p-values. Like that. And you look at the literature and you're like, that's weird. Why is there such a big jump of people getting p-values just under 0.05? Is it because they're cheating and they're liars and they're bad scientists? Yes. But they're only bad scientists because the reviewers are bad scientists. and we have bad incentives. So, anyways. Now, I realize we're out of time, but the last point I'm going to make is I can conclude that these distributions are different, but now what is the effect size? Imagine I'm running a business and I want to make a change, and I can conclude that, oh, if I make this one change, I will get different results. But maybe it costs me like $1 million to make that change, and the amount of change it has, the effect of that change is actually kind of small. So even though it will give me different results, how much better are they? And this is where you can do a Cohen's d. I'm pretty sure this is the right one. Hopefully I'm right. All right, well, if we go here, this explains it. I'll do this at the beginning of next class because we are out of time. But you take the absolute, or you take the difference between the two and divide it by the standard deviation. I'll explain it later. Anyways, we'll end here.